All right, lab one, constant velocity. Let's get into it. All right, so basically, a little background about this lab is, we're recording a moving object. It's moving at a constant velocity. And then using tracker, we can create a position versus time chart and use that experimental data to construct a computational model. Then we compare these two models and then see how Newton's second law applies to both of the models. Now, it's important. Newton's second law is important because it shows a relationship between a force applied and motion, more specifically acceleration. But anyways, as you can see here from this equation, Vf equals Vi plus F net over m times delta t. So basically, in this experiment, we want F net to be 0, because when F net is 0, the velocity final will equal the velocity initial. When F net is not 0, this will not be true, and therefore there will be a change in velocities. With that background info out of the way, we can now move on to the experiment and the data. So basically, my experiment was rolling a soccer ball, and then tracking the motion of it, and putting it in tracker, and this tracker gave me a position versus time chart with some values there. And basically, we can use the values to calculate the velocity at which the ball is going. So as you can see, I tracked it from a couple frames in, so it would have the acceleration out of the way. And getting the position over the time, I ended up getting the vectors of 1.88 meters per second, 0 meters per second, and 0 meters per second. And then the velocity here will be the initial velocity component for the computational model. So with the information that we just found from the experiment and from tracker, we can create a computational model using the provided code. And so basically here, we're using the velocity that we found from the video analysis and inputting that into our ball velocity, which will be our initial velocity. And something important to do here is to set the net force equal to the vector 0, 0, 0, because theoretically, in order for the final velocity and the initial velocity to be equal, the F net vector has to be 0. So, as you can see, the position versus time chart that the model prediction inputs out looks awfully similar to the one that tracker inputs. However, this one is 100% perfect with no net force affecting it. So, let's compare these two graphs. Now, we can put the model and the experiment charts together in order to better compare them. So, as you can see, I have done that here in a position versus time chart. And the model data has a constant positive velocity, while the experimental data has a positive velocity. However, it is not constant. In fact, it is fluctuating between time intervals. So, why exactly is that? Well, it's because in the experiment, there's no way to control the net force. In the model, the net force was always coded to be 0 newtons. So, since the velocity slope is slightly lower for the experiment than in the model, I can make the conclusion that there are forces acting on the ball, causing it to slow down. Most likely, these forces are the force of friction, the unevenness of the ground, maybe air resistance. As you can see from my picture I put there, I put the axis, and some of the tracker dots that I placed are above and below the axis, which also shows human error. So, what if when we analyze the data, we actually wanted to flip around the axes? So basically, make the ball move backwards. How would the position versus time graph look like? So I've actually graphed it here. I've drawn a graph here. And as you can see, the positive constant slope shows the positive x-axis if the ball is moving that way, and the purple line shows the negative x-axis. So basically, if the ball is moving backwards. Now, since they have the same slope, but negative since the movement would be in the direction left of the origin. See, as you can see, it's always important to remember that in a position versus time chart, the slopes determine the direction of the ball. So basically, if the slope is positive, it's going in a positive direction, so to the right of the origin. If there is no slope at all, so if it's constant, the ball is at rest. And if it's going downwards, if it has a downward slope, it's going in the negative direction. So basically, yeah, and just in the negative direction. So another great question is it possible for us to say how many pushes and pulls are together to give zero net force in the case that we observed? Actually, we cannot, and here's why. So if the net force was equal to 0, theoretically, the velocity final and the initial would be equal to each other. This would create the constant positive slope. However, due to the other forces that are in play in our experiment, for example, friction, air resistance, This is hard to accomplish. Actually, it is 100% impossible. And this is because we can never get rid of the force of friction and things like that. And we could see this in our experimental graph because there is not a constant velocity. In fact, it fluctuates. So it is not possible to add together all the forces that would give a zero net force. Um, but the whole importance about learning about Newton's second law and the importance of this experiment is to understand that the forces applied on an object result in motion, and controlling and measuring the net forces can help us find acceleration and velocity, which is useful for engineers to map out trajectories and to find the position of an object at any given time. With all that being said, that concludes the first lab.